stage 3 opponent challenge the reporter for the problem.
Problem 2, air muscle. Problem 2, air muscle.
Problem number 2. Problem number 2. Air muscle. Okay. The reporter 6 minutes.
I reject the challenge.
Okay. The reporter rejects the problem number 1. Oh, number 2. Sorry, number 2. Reject number 2. So, step please. Reject number 2. So, could you change the challenge to another problem?
We would like to challenge problem 9, magnetic assist.
Okay. Problem number 9, magnetic assist. And the reporter accept or reject problem number 9.
They reject.
No, not yet.
I accept the challenge.
Okay, hold on. The reporter accepts the challenge problem number 9. Okay. Now the preparation of the reporter 5 minutes. And each team write down the represented name on the blackboard. Thank you.
这是第9题哦。
哎，5分钟。
呀，他没有给你，
对，这个 OK。
可是他没有，
哎，你说那个没有在跑？
就是他没有取消掉2。哎，这里有3，这里有3，就是，
要不要找
这样
吗？
是
李彦昌、陈孝全、蔡美芬。 Okay, so now it's a presentation of the reporter, 12 minutes.
Okay, so I'm from Timber. Hello, I'm from Timber. And the topic I'm going to introduce is a magnetic system. It is a proper statement. It says we attach only two magnets on a magnetic and non-magnetic base, so that we can attract the magnets on the base system from the stick. I'm going to investigate the motions of the magnets depends on the relevant parameters. And for observations, I assume several forces we consider in the motions. First is the tension come from the string, and the mass of the magnets and the magnetic force. And this is my outline. For observation, it is a break experiments with no magnets on the pendulums. And for setup, I release the pendulums by the tweezers and attack the cameras from up to down to overlook the whole motions of the pendulum. And for the right side of my report is the length of the pendulums I use, and it is 125 centimeters. I believe that it is long enough to control the direction changes between the magnets moving. And this is my simulation code. Then I consider geomagnetism affects the motions of pendulums. As you can see, the NA size is much predictable with the EW size motions. So I believe that the geomagnetism should be considered. So for the following experiments, I will do the NA size. Then it is a quantitative motion. For the motion, it is a normal pendulum with no magnetic attack on the base. And then I'm going to attack one or two magnets on the base and investigate the trajectory affected by the attraction. And then I assume several regions in my motions. First is a simple pendulum. For it, restraints a small pendulum is that the affected by the magnets on the base is less just because of the higher energies of the pendulum. Then is the patterns. And for patterns, the magnets on the pendulums is affected by the magnets on the base more. So it will change the directions between the motion. And for the last one is the attraction patterns. For the attractions, as you can see, the magnets was tightly attracted by the magnets on the base. Then is a commutative motion. For commutative motions, I assume several things. First is the L represents the length of the pendulums, and the H represents the distance between the lowest positions of the pendulums and the magnets on the base. By using both things, I could guess the distance between these two magnets, which are shown as the R. Then this is all the force I assume affects the functions. First is the attracting force between the magnets, and the eddy current force is the mass of the magnets and a resistance. First, I'm considering the attracting force between the magnets. For the attracting force between magnets, I use the equations which are shown as the capital RTs of the magnetic field, and then I replace the direction of magnetic fields. And for the right side is the calculations of the magnetic fields to get the magnetic dipoles of the magnets I use. And then this is a magnetic force. And for assumptions, I'm going to consider eddy current force. And for eddy current force, I use the equation which are shown as the JADs. And then I replace the J is at the Maxwell of Gauss's laws. So for the right side of my graph shows the calculations of eddy current force. As you can see, for the left side of the graph, it shows the pendulums which are only affected by the eddy current. So I believe that the eddy current should be ignored due to the graph is just like a single pendulum. Then this is all of those I consider in my motion. And I could get a function like this. And then I use so this is the equivalence of my motion. So first there will one magnet attack on the base. And then there are several parameters I will do is the different heights and different positions of the magnets on the base. And for a different height, I do several independents. First is 3 centimeters, 4.5 centimeters, and 6 centimeters. And I'm going to track the motions of the magnets I use. And then this is 6 centimeters motions. And this is 4.9 centimeters motion. And then this is 3 centimeters motion. Compared to those motion above, I can get added a trajectory of different motion together. As you can see, the red line which shows the 3 centimeters magnets was much more at the same directions because of the attractive force is more significant affects the trajectory of the motion. And then I'm going to consider the Laplace exponents as the report above. When the lambda is less than 0, it is a stable motion. And when lambda is more than 0, it shows the chaotic motions. And for a calculus of my experiments, different colors means the different times I do my experiments. Then it's the different positions. Then it's the positions with velocity and 0 and 0. Then it's the positions with 0 and 5. And these positions with 0 and 10. And this is the positions of 5 and 0. And this is the position with 10 and 0. And then this is the trajectory at these several different positions together. Then these are experiments with 2 figs. Okay, so with the 2 figs first, I'm going to experiment with different heights. With the 3 centimeters, 4.9 centimeters, and 6 centimeters. And independent variables is that I'm going to track the motions on the magnets. And for 6 centimeters with two magnets experiments. And this is 4.9 centimeters with 2 magnets together. And this is 3 centimeters. Sorry. And these are 3 centimeters with 2 magnets together. And then for the left side of my course, this is the graph which shows the 3 centimeters motions. And for the right side, I use the simulation as I showed for above of my reports to simulations the motions of the pendulum. Then there is an experiment about different positions with 2 magnets. First is the 2 magnets which are different positions are phi 0 and minus 0, minus phi and 0. And this is 0, 5 and 0 minus 5. And this is 0, 5 and 5, 0. And for conclusions, there are several regions I assumed. First is the simple pendulum regions. As you can see, the motions are just glued together as simple pendulums. And then for the middle size is this whirling regions. And as you can see, the magnets was doing just like a circle. And for the right side is attracting motions. for reports, I do various parameters. For the left side, it is the difference magnitudes, is the attractance between these two. Is the difference heights between these two magnets, which are shown as a trajectory comparison with different magnet heights. And as you can see, the red part is 3 centimeters with magnets, and the blue part is 400 centimeters with magnets. And as you can see, the red lines is much as you can see as the same directions than the other lines. And for the right side is the different positions. And as you can see, it is such a very huge effect by the different positions. Okay, so also in my report, I do the Diagonal experiments. And to my opinion, the Diagonal experiments represents that I can calculate what the initial conditions affect the following motions. So as you can see, I have calculated my different experiments between my reports. So and by calculating the different initial conditions, I can get the Diagonal experiment. And that's all my report.
Okay, thank you. What is the question of the opponent to the recorder? 2 minutes.
Our first question is, did you consider the damping effect of the magnets?
Yes, I consider air resistance and add it to my equations of motion.
So were air resistance your only damping effect?
No, I also consider attractive force between these two magnets will affect the oscillations of the magnets in every moment.
Okay. Is there a boundary limit for, according to your parameters, there was one like 4.5 centimeters, 6 centimeters, and 2 centimeters. Is there a boundary limit for that?
So could you pass me the parameters?
The parameters. Is there a boundary limit for your parameters for those different centimeters? Is there a boundary limit?
What is the parameter?
A boundary limit. And then, never mind. Did you ensure that your release point is the same?
Yes. I just due to
Did you ensure that your release height is the same as well?
yes.
Okay. Were all of your experiment observations having chaotic behavior?
Yes.
Do you think that the Earth's magnetic will cause some deviations to experiments?
What do you mean?
They're like because Earth itself is like a magnet. So do you think it causes?
Yes, I consider it.
You consider it.
Yes.
Do you think it causes deviations?
No, I just do it as this size is much linear than the other size.
Okay, thank you. And how did you ensure that your string was straight throughout your experiments?
Yes. I also add some mass on the magnets, which is made of wood. So it was I didn't see it weak enough to make the thing won't become shorter. Yes.
Okay, thank you. Now is the preparation of the opponent. 3 minutes. Now opponent takes the floor.
Honorable juries and fellow competitors, I am the opponent from Team Excelsior, and for today, I'll be opposing problem 9, magnetic assist. The problem statement reads, attach 1 or 2 magnets to a non-magnetic and non-conductive base, such that they attract the magnet suspended from a string. Investigate the motion of the moving magnet and depends on relevant parameters. And for today, we'll be mainly focusing on how different parameters affect the motion of the magnet, and what boundary and deviation will affect the motion of the magnet. This is a reporter's outline. His theory included the magnetic attraction and forces, and he also analyzed the motion dynamics of the moving magnet, and he also discussed about the magnet alignment effects. And for experiments, he did the length of the magnets, and we'll discuss about the parameters of the opponent later. And for controversy and deviations for the opponent's report, there could be consistency of the magnet polarity that could be considered, and there could be some environmental interference, for example, like vibrations, that could be considered, and the stability of the motion could also be considered, meaning the stability and how stable the magnet moves. And there could also be some deviations in the variations in the magnetic strength. Okay, so here is the strong and weak points for the reporter. He provided a very clear observation video, and he also explained the magnetic chaotic phenomenon well. However, he had a lack of fairy line, and he had a lack of explanation of the possible deviations. And he had a simple but clear qualitative explanation, and we like to ignore this part. He had a lack of error bars for his report. And next, the opponent would like to talk about what we will be discussing about later in our discussion. First of all, we would like to talk about the setup for the magnets and for both the pendulum and the bottom magnet. And we would like to talk about the interaction between these two magnets, of course, which is the phenomenon itself. And we would like to also talk about the measurement of the motion speed or the distance, how you measure these data. And we also like to talk about the magnet alignment control. How did the opponent ensure that your magnets were aligned with each other? And we would also like to talk about some possible damping effects, which would include friction and air resistance. And we also like to talk about the boundary conditions that the opponent didn't really understand in a question previously. And for theory, we would like to mainly talk about the chaotic behavior of the magnets, and the energy conservation and the transformation between energy. And for the parameter, we would like to talk about the magnetic strength, how it has changed the phenomenon, and the mass of the moving object, how will this affect the phenomenon, and the magnet orientation, meaning the spinning of the magnet itself. And also we would like to talk about some relevant environmental factors. If we alter these environmental factors, how would these factors change the phenomenon? And we also talk about length of the string. And we would like to start our discussion.
Discussion with the reporter.
Okay. So in your previous questions, you mentioned that you ensured that the release height and the release point of your magnets were the same every time. So could you please tell the opponent how you ensured that?
Okay, so to my experience data, first my experience data, I released the magnets by the tweezers. Okay, so as this, I release the magnets by the tweezers, and also by control the different heights of the by control different same heights of the tweezers. I can control the distance between the central part and my release points.
You mentioned that you used a twister to ensure that it was in the same place. Right?
Yes.
Can you please, Juries, will you please use a whiteboard?
Yes, please.
Would you please give me a graph of your twister?
Twisters.
Yes.
Okay. Hold it. But there were I attack a mood up above, as you can see, and then there were just a attack. There were these tweezers. Yes, these are tweezers, and I have a tab here. And by control, there are the magnets just putting us here.
Okay. Regarding your graph, you mentioned, this is your twister, am I correct?
Yes.
Okay. The definition for chaotic behavior is if you alter even just a little bit of the initial conditions of your experimental experiments, it would alter the entire outcome or the entire process of the entire phenomenon. So would you think that you would cause some deviations when there's like a little bit of, for example, how do you ensure that you release your magnet in the exact same position every time you conduct your experiments?
So just because I do my best to control initial conditions, but just because the very small changes between the initial condition I release and we could cause the belonging health system. Yes.
So do you agree that this would be caused by a chaotic system?
Yes, I do.
But why did you say that you ensure that your release time will be the same? Because
It will just be
release points, I'm sorry.
release points will be really close to each point.
Okay, but as I mentioned before, chaotic behavior defines as if you change just a little bit of your initial conditions, it would change the entire outcome. So wouldn't you think that just making sure it's close and not exactly the same be a very big deviation to experiments?
Okay, so it means that I would like to move this step between these two, just like one simple resource between these different experiments. So I think for this experiment I will do in the future. Yes.
Okay, thank you. Would you please turn to page 51?
51.
Could you please? Okay, yeah, thank you. Regarding your experiments and your theory, I still see some, especially over here. I see some. Your experiment conducted shows a rather stable line for your graph. But what about here? You said that your experiment matches your theory. However, the opponent does not see how it matches perfectly or relatively the same.
So my summary maybe has some things to change just because there was something like just like this. Yes, and maybe I will do it in the future.
Okay. The opponent would like to suggest that the reporter provide an error analysis in the future to ensure that to explain or to ensure why your experiment does not exactly fit your theory. So we understand this problem better.
Yes.
And Julius, will you please use the whiteboard again?
Yes.
Could you please draw what specific magnetic force drives the motion when magnets are involved? First of all, let's think about one magnet.
What do you mean attracting force between magnets?
Yes, can you draw the specific force analysis of your phenomenon?
Okay, so this is the pendulum, and there were magnets like this. And I believe that the attracting force is between these two magnets. So I assume the positions of the magnets above, and the positions of the magnets on the pendulums, and do my series. And this is
Sorry, I think the reporter misses the reporter would want to add, the opponent would like to ask, can you draw the forces that drive the entire motion? Like, could you please like demonstrate, like for example, there could be like damping effects over here, and of course there will be magnetic attraction toward the bottom magnet. So could you please draw and demonstrate?
okay. I'll try to use the whole force. So this is the magnets, and this is the magnets on the base, and there is an attracting force between the magnets. And also there were air resistance as the magnets. And also there were mass of the magnets. And also there was a tension caused by the string.
Is that all?
Yes.
Okay. Could you please tell me first of all, where did you say you considered the damping effect of
So sorry, what do you?
Okay, so you mentioned that there's air resistance,
Yes.
like being damping. So could you please tell me where in your report, or could you tell me now, how does it affect the motion? How does damping affect the entire motion, and could you quantify it?
Okay. So first is air resistance, and second is the attractive force between the two magnets.
Let's just consider damping for now. Just air resistance for now.
Okay. So for air resistance, I've used my previous experiments with no magnets. Yes. Excuse me. What do you mean by figure difference?
No. I mean, can you please tell us what are the causes? How does damping affect the motion, and can you quantify the damping effect?
So you mean that when the pendulum moved, there were dampings affect the moving pendulums, and so there was the attractive force between these two magnets will be more significant.
Be more significant?
Yes.
However, the opponent believes that air resistance is actually going against. Oh wait, you said more significant? Okay.
Yeah. If you make the attractive force between these two magnets more significant, affect the motion of the pendulum.
However, the forces are supposed to be the same because they are the same magnet. Does a reporter mean that it will be more clear that they are attracting each other?
Yes.
Okay, so
So I have several references in my model. Yes.
could you please turn to a place where you said you attached a mass to the magnet, I believe? Okay. So, regarding your you applying a mass towards the magnet,
Yes.
did you ever conduct an experiment without the mass? Did you say you added an extra mass
Yes.
to the magnet?
Yes.
An extra mass. So, first, well, can the opponent please ask why the reporter did so? Why did the
You
reporter?
mean why I add the mass at the
Yes.
Yes, I just want to ensure that the stress won't just like not linear, unless as a linear line.
However, the problem statement did not ask to add a mass. So, wouldn't you think that adding a mass to the bottom affect the entire motion when it's not supposed to have a mass?
Okay, so just as you can see, the attractive force wasn't just the cause the tangential oscillations, but also cause the tangential oscillations. So it's by causing the tangential oscillations, the strings there won't cause. So I will add a mass to it. That is much mass to it.
So, did you conduct an experience to prove that without the mass, the motion will be the same?
No, I want to make that do it in the future.
Okay, thank you. The opponent advised the reporter to do so. And how did you ensure that the magnets are aligned to each other?
What do you mean?
Could you please turn to a page where the reporter said he aligned the magnets? Experiment where this pendulum swings in this way. Okay, never mind. How did you ensure that these two are perfectly aligned with each other?
You mean the magnets on the base?
Yes, exactly.
Yes, I have just the lines as the 5.5 centimeters. I mean that's just like I place A4 papers above. This is A4 papers above, and I have just A4 lines with the distance was 5 centimeters.
Thank you. Opponent summarize the discussion.
Alright, so in our discussion, we first talked about the initial conditions which would affect the chaotic behavior. So we first talked about the release point and also the Toysler. We can also cause some deviations to the reporter's experiment. And the answer was yes. And the reporter meaning that the reporter couldn't control the initial conditions perfectly, meaning there could be some deviations that were caused not just by their parameters, but also by their chaotic behavior of the phenomenon. And for the third point, the reporter's unstable line can match the experiment and then explain the error analysis. So the opponent showed the graph on his report, and there were some differences between the theory and the experiment. So the opponent suggests to have an error analysis next time. And we agreed that the damping effect is caused by air resistance, and we agreed that the extra mass probably will cause influence to the motion.
Okay, now the reviewer question.
The question for reformer and opponent. Do you think the chaos has exactly definition?
What do you mean exactly? The definition of chaos.
Yes.
Oh, I use chaos definitions is because there was there very small difference with the initial conditions. So it will cause the following motions will very have a significant change.
The opponent would like to have a small disagreement with the reporter. Chaotic behavior defines that if there is any initial condition changes, it will change the motion and the phenomenon.
Okay,
So,
thanks. A question for both of you. How do you define the little difference?
Okay, so I define the little difference means that I have do my best to control the initial conditions. So by little effects by the currently same.
Okay, thanks.
little changes could be anything. Like it could be the difference in temperature, differences in location, or like just 0.1 millimeters could cause huge deviations and huge
Okay,
changes.
thanks. The question for opponents. The reporter used the Lyapunov exponent to prove the magnetic pendulum is chaos. Do you think the Lyapunov exponent is suitable of this experiment?
The opponent believes that there could be some non-suitable parts for using that equation and that theory for his experiments, but however, it's mostly suitable.
Okay, thanks. Do both of you think that there's a critical value between the chaos and not chaos?
Yes. Rephrase your question.
Do you think there's a critical value between the chaos and not chaos?
Yes, the opponent believes so.
Okay. For reporter, do you find the critical value between the chaos and not chaos?
No, I didn't find it.
Okay. The next question. The reporter recorded trajectory on the top view. Do you think the high difference will cause the trajectory data inaccurate?
You mean? Yes, is it high sensitivity or high resistance? Is it?
Okay, thanks.
Could you just repeat it?
Do you think the reporter recorded trajectory on the top view? Do you think the high difference will cause the trajectory data inaccurate?
Yes, there could be some deviations incorrect.
Okay, thanks. When we put the two magnets on the base, the magnet will stop on the same magnet or not?
No.
No.
How do you think if the trajectory difference but the result is the same? The magnet stop location.
Thank you. Preparation of the reviewer. 2 minutes. Now the reviewer takes the floor. 4 minutes.
Okay, hi everyone. I'm the reviewer from T101 and we'll review the problematic analysis. And above this problem statement, we mainly focus on the trajectory of the moving magnets and how the relevant parameters affect the magnet's trajectory. And this is a review of the report. In a theoretical model, we use the force analysis, magnetic currents, and the Lyapunov exponent. The process is real explanation in force analysis. But the Lyapunov exponent doesn't fit the theory because the trajectory will eventually get up to 1 point only. And they didn't define the definition of the chaos. And on the experiment data, he used a different position between the fixed magnet and released magnet, and different number of fixed magnet. And different positions. Okay, the process is a good method for controlling the magnet release. And but he considers he wrote them not enough, so he should consider the axis movement. And also the rope vibration will affect the results. And about the data analysis, they focus on the trajectory of the moving magnets. And he done experiment multiple times to compare the trajectory. But he showing the XT and YT data can clearly explain the whole trajectory. And this is a review of the portion. And the short question is each time that the opponent asks about the air resistance position of the magnet's release height and chaotic. And he clarifies the method to release the magnets and also clarify the calculation of the ampere force. But he didn't clarify the definition of chaos. About the key discussion, they discuss about number derivation, magnet orientation, and environmental factor, then strength magnetic force calculation, energy conservation, and role of magnetic orientation. The process mentioned a huge effect from air resistance and state the definition of the problem statement. But the lack of a discussion, what is chaos, and also lack of a discussing trajectory graph. And about the key discussion, the discussion about how the stamping affect the motion. The report said it will affect the attractive force. But I think damping will affect both attractive and repulsive magnets, and it will also constitute an effect on the trajectory. And then also talk about the release location. The reporters try their best to control the release location, but I think there's not really accurate because the chaos is very sensitive to the initial conditions. And about our question, I asked about the diagonal formula will freeze the phenomenon. The opponent said not in very condition. I think this is not fit in this experiment because the Lyapunov exponent is used to the bifurcation of the experiment. And there's a question about the critical value. I asked about there's a critical value between the chaos and not chaos. The opponent says yes, and the opponent says yes, and the reporter says yes. The reporter also said they didn't find the critical value between chaos and not chaos. And I also asked about the definition of the little difference because the chaos is very sensitive to the initial condition. But I think the little difference is very small, so when we control the release location, so it will cause the chaos. And about the missing points, the reporter used the wrong ways to prove the chaos is happened during the experiment. And they didn't mention about the torsional force which from the magnet's location. I think that will affect the magnet's trajectory. That's all. Thanks for your attention.
Okay. Now the concluding remarks of the reporter. 2 minutes.
Okay, so my conclusion to my report and the conversation between the opponents. First, for my report, I do the first analysis of the magnets, and I just do the 3D modeling, and I consider eddy currents and loadings. And also, I do several parameters, which is different heights and the fixing amounts of the magnets and the positions of the magnets. Also, I do the opponent's experiments to make sure the motions of the magnets I use is a chaotic motion. And also, the simulations I do is matched to the degree sent to the experiments I do. And also, I have to do several times in each experiment to calculate the Lyapunov experiments. And also, during the conversations with the opponents, he asked me about the chaotic experience. And And to my opinion, the chaotic means the motions was sensitive to the initial conditions. So due to the little movements of of my release point, it will cause the hugely affects the following motions of the trajectory. And for a release wave, it is really a small difference between these two release points. So it will cause the following chaotic systems. And also, he asked me about the damping magnets. And I believe that the damping will cause the distance between these two magnets very close. So the attractive force between these two magnets will be more important. And also, he asked me when we are at the mass on the magnets, what will it cause the effects? And I believe that I can do it in the future. And also the trajectory. And that's all my summary.
Okay, thank you very much. So now the questions of the jury. Yeah, 李老师。
First, I have a question to report to. Like you point out, there is a eddy current.
Yes.
So can you explain how the eddy current affect the results?
So we was the editor.
How the eddy current affect your results?
So due to the changing position between these two magnets, it will cause the changing magnetic difference between these two magnets. So it will cause there was currents on the magnet, on the moving magnets. So it will affect the trajectory. But it was very small as I calculated, so I will ignore the current force.
So does it affect your result?
I just calculated that it is very small to be. No.
So it's not affected.
Yes.
I have other question for the viewers and opponents. Like, if we only consider one magnet-based system, and we release the pendulum with the same position, do you think that the time for this pendulum to stop versus will be the same or not?
Would the jury please define is, do you mean like exactly the same spot?
Yes.
Well, it also has to do with the extra force you provided to the magnet. If you just released it, the opponent believes that it wouldn't be too many deviations. It would be the same every time if it's exactly the same, and only exactly the same.
So how?
Also, sorry, there is the question again.
Repeat your question.
Sorry. If we only use one magnet space and we release the pendulum at the same position, do you think the time for this pendulum to stop, finally, eventually it will stop, right?
Yes.
The duration of time is the same or not?
I think it's not because because when we release the magnets in the same position, and I think the magnetism will affect its trajectory, right? And I think the magnetic force will increase the moving magnet velocity and also decrease it. And I think the degree that effect is not the same. So I think during the motion, during the magnet start moving to the magnet stop, I think the time phase will not the same.
Question from the jury.
You consider the trend non-competitive delay
The plane is the surface.
Yes.
Plane. For this question, the base is a plane.
Yeah.
Right?
It's absolutely terrible.
In this question, the base is the plane. Oh, so the jury say if we put the magnet two-dimensional plane array, right? Array. Do you know array?
Yeah.
So
Array of
magnets
magnets.
horizontally and vertically array. If we have the two-dimensional magnetic array, what do you expect for this motion? Oh, interesting. Two-dimensional. So yeah, think about who want to answer.
I would like to ask the jury, what does mean by 2D magnetic plane?
Just to put the magnet array.
So you mean a lot of
A lot
magnets?
of magnets.
A lot of magnets on the
And then
same.
you still have pendulum go through this 2D magnetic array. What happened?
So first, the opponent would just like to clarify that in the problem statement, it only mentioned one or two magnets, which is why we didn't at all first consider that there were a lot of magnets. However, the opponent believes that it could be observed as chaotic behavior when just only two magnets are in place. So if there's an array of magnets, it could definitely be chaotic behavior.
Yeah. So do you want some
Yes.
add some comments for this?
I think it will cause the result is not different. It will, because the problem statement it give me the magnet number. But when we put the magnet in a array, so I think that it will cause the result more chaotic.
More chaotic. So reporter, do you have any comments for this question?
So in my opinion, if the densities of the magnets you put is very high, the difference, the two attraction force between the magnets will be very little difference. So when the mass is very large enough to make it more bigger than the difference attracting force between magnets, this will be stopped as the middle spots, just because the mass was down.
Thank you for your answer. Thank you. So now is the grading for the jury. The grade for the grade for the reporter 6, 7, 6, 7, 6. Yes, correct. And the grade for the opponent 6, 7, 8, 7, 8. Okay. It's good. Right, it's correct. And the grade for the reviewer 6, 6, 8, 8, 6. Okay, correct. Okay. Any comments?
I have one additional question for the reporter, like what is the material, this is not related to the what is the material used for the magnet?
Material of your magnet. Huh? Element.
This is not lecture because you mentioned this. I heard the magnets for many times. And magnets is one kind of element. You say magnets. Magnets is so magnet is not magnets. Magnets is some kind of element.
Be careful. Okay. Thank you, Li Lao. So let's take a 10-minute break.